In this problem, we are given the following circuit diagram here. We were also given our voltage in the sinusoidal form. We are asked to find the value of the inductance, which achieves the given condition, and find the circuit's impedance at the value of the inductor found in part A, and then also find the current I of G as expressed in the time domain as the inductor value of part A. We're also told that the variable inductor is adjusted until the current I of G is in phase with the sinusoidal voltage. This is very important because it's going to allow us to set our imaginary numbers equal to 0 so that we can find our L. And this will come important later in the problem. First, we're going to start off by solving for part A. In part A, we need to find the value of our inductance. Well, to do this, I'm actually going to write a formula for our Z equivalent. We are going to solve for all the impedances, and since we know this impedance and this impedance, the resistor and capacitor, we may be able to find this impedance, which is our inductor. For a capacitor, when we are writing it as an impedance, we are going to have our Z of C equal to a negative J over our omega times C. And for our inductance, we know that we have a Z of L is equal to our J times our omega times our L. We know that we're adding the capacitor to our parallel part, which has the inductor and resistor in it. So we're just going to have our Z of C plus, and since these impedances are in parallel, we will have 1 over the first impedance plus 1 over the next impedance, and our parallel part is raised to the negative first power. Now that we have this, I'm going to substitute in for our Z of C and our Z of L. We know that our Z of C is a negative J over our omega times C, and our Z of L is equal to J times our omega times L. Now we're going to write this as one expression and then flip it over because of this negative 1 as the exponent. This is going to be our new equation. Now we need to combine this part and this part together, so we are going to do the same thing where we multiply these two and then multiply the denominators together. And obviously we will add the numerators together as well. Now from here, we want to set our imaginary numbers equal to 0. We can't do this when we have substance like this in the denominator. We have our imaginary number here, therefore we cannot do this. So what we need to do is multiply everything and get rid of our J, or the imaginary part, in our denominator, and then we're going to look at all the imaginary parts in our numerator. To do this, we are going to use the following equation here, and we will factor this in, and then we will get a new expression after this. After we do this, we will have the following equation. We are now not going to look at the bottom part because there's no imaginary numbers in here, so we can kind of cross this out, not look at it. And then for the top part, remember, we only want imaginary numbers. And in fact, we can cancel this out with this because one is a positive and one is a negative. Now we are going to see this last part doesn't have a J in it, so it's not an imaginary number, so we will not be looking at this part either. Now that we have all of the parts with our imaginary numbers in it, we can set this equal to our 0. And then we can proceed to rewrite this equation. And this is what we have. So from here, I am going to cancel out our J's, since there's J's and everything. I'll just divide it out. And then after this, we can see that we have a capacitor in each of these. So I'm going to get rid of the capacitance here and the capacitance here and set this capacitance to just 1. So we're just going to have a C1 in here. And then I'm going to do something similar with our omega. We have an omega here, and then we have one here that I'm going to make a 2, and then same thing for the omega here. Now I'm going to rewrite this equation. This will be our equation. We want to solve for our L, so I'm going to move this out front, and then plug all of our given values into here. Now this will be our new equation. And then we can plug all of this into a calculator using the quadratic formula. So this first part is going to be our A, this next part will be our B, and then finally this last part will be our C. After we plug all of this into a calculator, we are going to notice we have a slight issue. And the issue stems from the square root part. And this is because what is inside of our square root is actually a negative, and we can't square root a negative. So we're actually going to have to break this apart when we're doing this with a calculator. That way we don't get a error. So the first thing that I want to isolate is this b squared minus 4ac. And that way we can make it into an imaginary number and then plug it into our square root. And in doing this, we're going to get negative 4 times 10 to the 12th power. We can see that now, if we square root it, why we were getting the error, because remember, we can't have a square root that has a negative inside of it. So what we can do is bring our negative out in the form of our imaginary number, which is j, and then we're going to have our square root of 4 times 10 to the 12th. And then we can also add in everything that we omitted earlier. So we're going to have our negative b plus minus our 2 divided by a. Now we can further break this up into two separate equations. We know we're going to have our negative b, and this is going to be over our 2a. We are also going to have our plus minus portion, and then we will have our j with the 4 times 10 to the 12th inside of it divided by our 2a. And in looking at this, remember, we only want the imaginary portion. So if we break this up, we are no longer going to be looking at this part right here. We are only going to be looking at this second part. And then from here, we are going to get two answers, obviously, because we have our plus minus. We are going to get a negative 4 if we have our positive, and then we are going to have a 4 if we use the negative. We know that our inductance cannot be negative because impedance, which is similar to resistance, cannot be negative. So that means we are not going to be looking at this negative 4 right here, and we're only going to be looking at this 4. So that will be the answer for our inductance for this problem. We have 4 henries. And that's how you would go about solving for part A. Now for part B, we want to find the Z equivalent. So what I'm going to do is take the equation that we wrote right here and plug in all of the values that we know. Now this is going to be our new equation. From here, I'm going to cross multiply these and add them together, and then multiply our denominators together so that we can combine this into one equation. So this is going to be our new equation. I'm going to take this part and then also this part and add them together since they are like terms. And then after I do this, I am going to convert them to the polar form. I'm also going to convert our bottom to the polar form. That way we can divide them out. And this is the, I guess, fastest way that you can do to divide something that is in rectangular form. To convert from rectangular to polar form, we're going to have our Vmax equal to the square root of our real number squared plus our imaginary number squared. We're also going to have our angle equal to the tangent of -1, and then inside of here we're going to have our imaginary number divided by our real number. And this is what we will get once we convert it to our polar form. Now, once we're in polar form, we are going to divide our numbers and then subtract the denominator from our numerator. If we do this, we're going to get approximately 1000 with 0 degrees. Now, we need to convert this back to our rectangular form because that's what we want for here. And to convert back to rectangular form from our polar form, we are going to have our number, and then inside of here, we're going to have the cosine of our angle plus j times the sine of our angle, and then in parentheses. And then if we do this here, we will get that our Z equivalent is equal to 1000, and then we have a 0j. So this is going to be the Z equivalent impedance over the inductor for part A. For part C, we are asked to find the current I of G as expressed in the time domain as the inductor value for part A. Well, we know that our current I of G is in phase with our sinusoidal voltage V of G. And since it's in phase, we are going to have the same max value and we're going to have the same angle. Think of it as if we were to draw a graph like this. And we know that normally our sine starts at 0 right here and it'll go like this. And normally our cosine would start like here and go like this. However, let's say our cosine is our current. And if it's in phase, if it's tuned to the same phase as our voltage, well, we could start our cosine current a little bit ahead. So we will move it up ahead, and our cosine current will start here, and then it will actually be the same as our voltage. So that means since they are the same, they will have the same values. So we will have a 100 for our current max, the same as our voltage max. And then we can see that we don't have any angle in our voltage. So we will have no angle, or we will have an angle of 0 degrees for our current. And that is how you would go about solving this problem. If you have any questions about this material, you can leave them in the comments below. If you want more network analysis problems, there will be a lengthy playlist with a ton more problems related to this and the entire coursework in the description. If you want notes for this material to study for it, there is also a Google Docs linked below the like button in the description that covers this entire course material.